Hello and welcome to hell. Calculus 2, Chapter 10, Sequences and Series chapter, right? The one with the bad rep. And I hope that this journey will not be painful, right? Please memorize definitions, theorems, and know your algebra, know your limits. And I mean, when I say limits, I mean mathematical limits, not the limits in other things. Well, you should know the other limits too. Whatever, know all limits, okay? So, to survive chapter 10, we need 2.3, 2.5, 4.7. All of these sections are in Calc 1, and all of them talk about limits. 2.3, basics of limits, calculations. 2.5, limits at infinity. All of our limits will be n goes to infinity. And 4.7 is the Hopital's rule. So mainly we are focusing on 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus, all of them. But most of the time you'll have 0 over 0 and infinity over infinity. All right, so to survive chapter 10, you really need to know limits. And you will be taking limits, let's say limit of n to the fourth plus 3n divided by e to the n as n goes to infinity, right? So when you have a problem like this, you would say you can solve this problem in two different ways. You can use the growth rate of functions, because what you learned in 4.7 is that polynomials grow slower than exponential functions, and because they grow slower, that means that exponential function on the long run, and you do have a long run, you're going to infinity, on the long run exponential function will win. Therefore this limit will be 0 just by looking at it, because you know that you have a slow growing function divided by a fast growing function. So in some sense, in 4.7, this is bad mathematical notation, bad mathematical practice, but it's true. So we're still going to write it even though it's terrible. Limit, and I'll put quotation marks around it, because if I was to teach in another country, probably I'll be dragged to the city square and shot for writing this, but you know. So limit of slow over fast is going to be equal to 0, and limit as n goes to infinity of fast over slow will be infinity. So as I said, these are terrible notations, but they do the trick in giving you the most powerful tool and the quickest tool to find the derivative. Now, the slow and fast are different type of functions. It doesn't work if you are comparing e to e, and because you do have the same growth rate. These are different growth rates between polynomial functions and so on. Now we will expand on it as we go through chapters here. We have the ln of n to be the slowest, and then faster than that would be some kind of the nth root of n, and then faster than that would be n to some power p, and then faster than that would be ln n times n to the p, and then faster than that would be e to the n, and then faster than that, one guy that it's new, n factorial, you'll see that eventually, and then finally the boss of bosses, n to the n. So this would be the growth rate. I'm going to put a question mark over here because you do not speak the language of factorials yet, but that is coming up today. so you don't have to worry about it. We'll cover it if you don't speak factorials yet. So this would be the growth. This is called the growth rate. Growth rates. And when I say slow and fast, I mean I am jumping from one to another. So I'm comparing two from this list, right? And now, if you are to prove this limit and do it the right way, right? The right way, you would use what we know as L'Hopital's rule. So limit n goes to infinity of n to the fourth plus 3 over n divided by, I'm going to regret this, e to the n. So L'Hopital rule says when you plug in infinity, you will get something. And if you get infinity divided by infinity or 0 divided by 0, which are called improper forms, you are allowed to take the independent derivatives. So it's not a quotient rule, it's independent derivatives of numerator and denominator, and the answer for that would be the same as answer for the original problem. So I will put L apostrophe H over here because I know I have infinity divided by infinity. When I plug in infinity, infinity to the fourth is still infinity, plus 3 times infinity is infinity, so infinity plus infinity divided by infinity. So I can take derivatives. You put L apostrophe H to say I'm using L'Hopital's rule, and you will take derivatives to get 4n cubed plus 3 divided by what remains, e to the n. Now when you try to plug in infinity, you still have infinity divided by infinity, which means you can use L'Hopital rule again. And that would be, yes. So it would be now 12n squared over e to the n. It is infinity over infinity again. So you keep using the rule until you run out of the options. And now you have 24n divided by e to the n. And you have infinity over infinity again because you have, right, when you plug in infinity, n is infinity. So, and this is going to be the last one, because now when you do L'Hopital's rule and limit n goes to infinity, you will get 24 divided by e to the n. And now you finally have a finite number, which is 24, right? A number divided by infinity. When you take a finite number and divide by infinity, you get 0. And the reason for that is, here is, this paper is from 2 years ago. I just dug it up in my bag so I can rip this. This is a unit of 1. I don't care if I have 1 paper or I have 24 papers, right? If I start dividing this into, this is divided by 2, and you see that the result is smaller than the original. If I divide it by 4, you see that the result is smaller than the original. If I divide it by 8, you see that the result is smaller than original. And if I keep dividing my original number by larger and larger number going to infinity, you see that your answers keep decreasing. If I start dividing by infinity, your answer will decay down into a 0. So the answer over here is 0 as you divide 24 by infinity. So this is the proper way to do the problem, but because, right, the Calculus 1 teaches us that every problem will appear the same. So when you have a slower growing function divided by the faster growing function, the faster growing function eventually wins, and you get to do the math, step by step all the way down when it twinkles down to 24 over e to the n, and then it's 0. So this is the skill that will be necessary for the survival in chapter 10. Your ability to take the limits as n goes to infinity, because what I mentioned is 100% of the problems is going to be, well, there will be some, introductory problems here and there that do not have a limit, but most of them will just, you take the limit and you go to infinity. Will there be some integrating? Yeah, but you know what what integral you're going to do? The improper one. So it still has a limit. So you will say, yes, integral test, finally off the limits, and then you realize that the integral test is going to be actually improper integral, so boom. Right? It's going to be 2 to infinity, and you still have to have a limit. So that's what I'm promising. I'm promising, 6 sections of limits. So please make sure you can do limits, and you can use your study plan in my MATLAB to go back in time and practice a whole bunch of limits, especially in 2.5 and 4.7. Those are those 2 sections will cover everything. Okay, cool. So now it's time for us to define the creature from the title, a sequence. Sequence is the ordered list of numbers. Is this on a test? Yeah. Statement. What is a sequence? What is a series? What is a monotonic sequence? Right? These kind of things. So there should be on test 3 a question that is asking you to state various things regarding sequences and series. So sequence is the ordered list of numbers. Now, what would be the word that we really want to pay attention to? Ordered. Thank you. Ordered. We all understand the list because we list things all the time, right? And then we all understand word numbers and so on. The word ordered, does it really need to be there? And the answer is hell yes, to the point where I like to underline the word ordered. So now, what does the word ordered means? Well, you understand that order, you sort people by age, you sort people by height, you sort people by weight, you sort people by income bracket, right? So there is some kind of sorting and there is some kind of order to that sorting. You don't just go onto the random place and just sort people. You cannot sort random. That makes no sense. There has to be some kind of criteria for sorting. And for us, in this case, ordering is done through the set of counting numbers, natural numbers. So order is achieved through n, which is the element of capital N with the 2 bars on the left side, and the capital N is the set of natural, I'll put in parentheses, counting numbers. So now it's time for us to see examples of sequences. Oh, let me also put notation. So notation for a sequence would be AN, and it would have, you can start with A0, A1, A2, A3, A4, and it will go on forever. Note that it is a list of numbers because I have commas in between, right? You will say that you would say, you have 6 sweaters, and one is red, and one is blue, and one is black, and one is yellow, right? And then the ugly Christmas sweater, right? So it's a list. You're just dumping numbers on a pile, but see, the trick is that all of them are in terms of I'm first, then I'm second, then I'm third, then I'm fourth, and so on, right? So there is order, which number goes first, which goes second, which goes third, and so on. And that will depend ultimately through the formula. It will depend and circle back to the set of counting numbers 1, 2, 3, 4, 5, 6. Yes.
I just wanted to ask, why do we go into the actual notation? Because they start explaining it in the chapter early on, but then you go back to chapter 5 where they start introducing the Riemann sums, and no one has any idea what's like n sigma k and all of those other things that go with the Riemann sum look like, and then they start explaining it.
The reason is that, unfortunately, education derailed. We are supposed to explain these basic concepts of the sequences and series in a pre-calculus course, because there will be no calculus for the first 15 or 20 minutes of the lecture, because we will be working exactly with the pre-calculus part. Now, as I said, education derailed because not everyone needs calculus, so why would we put these calculus topics on? It's a pre-calculus course. Why would you preheat the oven and never use it, right? There shouldn't be anywhere major or a program that requires pre-calc and does not require calculus. Just take stats, come on, right? But we do have some of those ridiculous programs that are requiring pre-calc 1 or pre-calc 2 without actually requiring calculus. So then the argument, so one bad idea snowballs to the next, right? So that's how you come up with this idea that you are going to go through the horrors of these things in Riemann sums in chapter 5 and not know what the hell you're doing. So now finally you get to see some basics, right? And say, oh, now the chapter 5 makes sense. That was your previous course, right? Anyway, let's put that aside now and go back. So sequence is the ordered list of numbers. And as the example, I am going to give a sequence an equals 1 over n. So this is my notation for the sequence. I am guys, you can read this as f of x, okay? It has the status of f of x because it gives you the formula on the other end of how to generate all the terms, how to generate the numbers that appear, right? So an is taking the form of a function, right? So, and generating formula is here. So now, what is the sequence? Well, if n, right, let's say n will start at 1, and then 2, and then 3, and then 4, and then 5, and then go, right, forever. So this will be 1, 1/2, 1/3, 1/4, 1/5, ... going to infinity. So this is what ordering is, right? Can you put these in other order? You can't. You can't. The order is going to be unique over there, because when you use the first number in accounting, and first number in counting is 1, right? Because I'm going to count the number of students I have. I'm going to start with 1, and then 2, and then 3, right? So when my numbering and counting starts at 1, then that n is equal to 1, and then I put 1 divided by 1 is 1. The next number in the sequence is 2. So 1 divided by 2, that's a half. And then 3, and then 4, and so on. So now you can create any formula. So the next example, you can use bn, you can use gn, whatever. So let's say you have 3n minus 1. You can do that, that's fine. 3n minus 1. So you can come up with any formula you want, and you have to check. Okay, now, this is the part where you just have to be a little bit careful, because now if you are running to write out this because you want to practice, and then you see that I start counting at a different number, you're going to be angry. The first example up there started counting at 1, because the counting does start at 1. And it would be the best galaxy ever if we always started counting at 1. But you can also start counting at 0. Now, the upper example cannot start count at 0, because you would have 1 over 0, and that would make everything explode, and there will be nothing left. Now, the bottom one can start measuring at 0. Now, see, this is that one thing that those of you who are in computer science already experienced. In array, what's the first location? 0 location, right? And you can start counting at 0 if the formula allows for it. So what are the rules? No rules. Good. So you can start your count at 0. You can start your count at 1. You just have to make sure that if you start your count with 0, it actually works out in the formula. So now, in this case, I'm going to start my count at 0. And have -1, and then 2, and then 4, no, lies, 5, and then 8, 11, 14, ... Could I have started at 1? Yep. If I start at 1, then the first number is 2, and then it will be 2, 5, 8. There is no rule. Now, if you streamline this and you say, well, counting really doesn't start with 0, because if I want to count the students here, I don't go 0 students and then 1, 2, 3, 4, 5. I go 1, 2, 3, 4, 5. So that is clear, right? But the reason why we now have to bend the knee to the second case is the computer science is starting arrays with A0. So, welcome to the chapter. Okay, so we specify where the counting starts. Even if it's not specified, you can pick one or the other. It's not a big deal. The situation where you get to pick where the count starts, right? You can just write down where you started your count. Did you start n equals 0, 1, 2, 3, or you started n equals 1, 2, 3? So it's not a big deal, right? We can deal with that. The next, okay, so let's have another example. So C of n is n e to the n, and we're going to start the count at 0. So give me first 0. Next one. Next one.
2e squared.
2e squared. Good. I know, right? 3e cubed. 4e to the 4th. Going on to infinity. Awesome, right? Woohoo! Is this a valid sequence? Of course it is. It's ordered list of numbers. I don't care what the output is. It's ordered list of numbers. And we used 0, and then 1, and then 2, and then 3, and then 4. So that in computer science, you can have your I++, right? To increase the counter for the next in a loop. So your loop in a computer science is always the next number in the sequence that will do the next calculation, right? Awesome. So now that we understand these, let's make it worse. We ordered so far by using counting numbers 1, 2, 3, 4. But in some cases, what you can do is you can come up with the next term by using the old ones, the previous terms. And that's called recursion. Do you all know Fibonacci sequence? Of course you know Fibonacci sequence, right? Mm-hmm. Fibonacci sequence says add the two numbers to get the next one. So start with 1, 1, and the next one is 2. Then take 1 and 2, make a 3. Then take 2 and 3, make 5. Then take, right, 3 and 5, make 8, and so on. So Fibonacci sequence is given as 1, 1, and then 2, and then 3, and then 5, and then 8, and then 13, and then 21, and going on to infinity. Fibonacci sequence adds two numbers to come up with the next. Fibonacci sequence is ordered right? So it's ordered. Fibonacci sequence is ordered, but it's not ordered through numbers. It's ordered through the what we call recursion formula. And now a to the n plus 2 is an plus 1. Okay. Welcome to Fibonacci sequence formula, and it's the first recursion formula you are going to see. Now I'm going to write some stuff in red over here. An is any term in the sequence. An plus 1 is the next term after an. I need you to understand this right now, because there is not going to be the rest of the chapter. What's written in red needs to be 100% understood for us to take any step further. So an is any term in a sequence. So it can be the fourth term. The fourth term is labeled A4. Oh, sorry, A3, right? Because A0 is the first. So if you want to talk about the fourth term, then in that case it's A3. And thanks, computer science, for that. So now, you have your fourth term, and you see that it has the index of 3, right? Because your first term is A0, your second term is A1, your third term is A2, and your fourth term is A3. So A3, 3 is the index of the fourth term. I increase that plus 1, 3 plus 1 is 4. That's the fifth term, which is next term. Okay? So all this says here is that an is any term, and then an plus 1 is the next term in the sequence. So then, common sense. I did tell you to retire. Just bring it back for a second. An plus 2 is the next term, right?
So then would we need to find an initial term?
They need to be defined to you. And I can put anything I want.
Well,
Fibonacci sequence is when the initial terms are 1 and 1.
Well, what I'm saying is, would we need like a function for an, for the series an?
You have the function. It's an plus 2 is for recursive function, and you have to define, right? Oh, okay, fine, you win. A0 equals A1 equals 1. There we go. Now that's Fibonacci sequence. Sorry. So, what did she find? So, she was probably going to say I found something interesting about Fibonacci sequence. So, you have to start the process. Just like in computer science, right? You have to give it initial, right? So the computer can keep computing the rest. Over here, I need the input of what are my first two terms in order to add them to create the next one, and then add to create the next one, and so on. So now, if I just write this 1, 2, 3, 5, 8, 13, 21, and let's say I take a look at these three terms here. This is my A0, A1, A2, A3, A4, A5, A6, A7. What I see here fits the function greatly. This is my A4 plus A4 plus 1 to give me A4 plus 2. This is, and you can see that's a 4, that's a 4, that's a 4, and if those are all 4s, it's then an. You can replace, anytime you have a 4, 4, 4 or whatever, you can replace with an, and that generates the formula that it's used. So Fibonacci sequence is not just a formula, but it's also that the two first numbers to begin with are the numbers that are starting the whole process, and used to figure out the population of rabbits and how they multiply and so on. But there is nothing that prevents you from changing the input values to, 7 and 21. And then you can start from there and create not a Fibonacci sequence. You will create something else that used the recursion formula. So recursion formulas don't have to be, it's not just Fibonacci sequence. You can make your own, right? Here, you can say that an plus 1 is equal to 3an squared minus 2an. And I'm just going to tell you that a0 is equal to 4. Give me the sequence. You have to compute, right? You have to compute.
24. So A1 is going to be 24.
24?
I did 32. That's 48. So it's going to be A1 is going to be 40.
So A1 will be 3a0 squared minus 2a0. A0 is 4, so 3 times 4 squared minus 2 times 4, because a0 is 4.
So it becomes 48 minus 8 equals 40.
16 times 48 minus 8 equals 40. So when I start my sequence over here, I will have the first number is 4, the next number is 40. Let's calculate another number. So A2 is going to be 3a1 squared minus 2a1. So that's 3 times 40 squared. Oh, that's going to be beautiful.
720.
720?
4,720.
Yeah, 4. Ah, yes, times 3. 4,720.
That next one I'm not there.
Well, yeah, then you have to square 4,720, right? Literally anything. You have to follow the rules that you will be using old terms to make the new terms. So we have these two types of sequences that we are considering. Ones that you get from counting numbers. Those are our first examples here, where you are using counting, whether starting at 1 or starting at 0. And you just use 1, 2, 3, 4, 5 to generate all the terms. And the second type, which is called recursive sequences, and those will use previous terms to build new terms. Your weather prognosis is using recursion because it is taking current temperature, which is occurring right now, and current air pressure and humidity and everything, and mushes that into a mathematical model to produce new set of numbers that are reported on the news. So it's an ongoing computer calculation which uses the current data to compute and predict the new data that is going to happen in the next hour, the next day, and so on. And these models obviously are improved constantly. So when you have to use old data to create new data, that's called recursion. When you are just using basic counting, 1, 2, 3, 4, 5, that's just, we call it just sequences. Great. So now I have to pull some of the problems from the book rather than break my head to make them. What we are going to do now is we are going to, caps lock is on. What we are going to do now is we are going to take a look at a problem which will have which will give you the sequences, and you have to come up with a formula for that sequence.
Could smell that coming.
So that's just taking the set of numbers and trying to guess where it goes to from.
Yes. So I will be giving you this, not for recursions, only for the basic ones that are, recursions. Recursions are.
I feel like I used to do these when I was like a kid, but like obviously really easy ones. But like, I feel like this is something I've seen before.
Definitely. All right. So get the AN formula given, and here is the sequence. So we will start with 1, 1/2, 1/4, 1/8, 1/16, 3 dots, goes forever. Make sure these curly brackets look half decent. Go away.
What?
So we did that with the problem.
Oh, did we? I can't remember that.
I want to say we did. Actually, now it's different. Never mind.
It's okay.
So what do we have?
1/2n. I think.
AN plus 1 equals AN over 2.
Hold on. So the first suggestion was 1 over, you said 2n, and you said
AN plus 1 equals AN over 2.
AN plus 1 is equal to AN over 2. Oh, you did the recursion on this one. Interesting. Okay. I said I won't be giving you any recursions. And the craziest thing is that your recursion actually works. But you have to define the first term. And you have to say A0 is 1. Otherwise, your formula doesn't work. I was looking for something like this. Unfortunately, this one doesn't work because if I start at where would I start? I'll have to.
0 equals 1. You can't. Okay.
If I start, you see, n equals 1/2, I can't start counting at half because half is not a whole number. So, I mean, it's getting there, but even if we are to kill 1, it would not work. Because if your n is 1, you get 1/2. If your n is 2, you get 1/4. If your n is 3, it's 1/6, which is not on the list. Aha. Okay, so 1 over... So this works, but let's see what is the explicit form rather than recursion. Any ideas?
1 over n.
Wait a second.
1 over n would be, you're missing a 3 already.
Oh, yeah.
Because it will be 1/3, 1/4, 1/5, 1/6, 1/7, then 1/8.
1 over n.
1 over n squared would be 1 over 1, 1 over 4, 1 over 9, 1 over 16. You're getting closer.
Getting there.
You are getting closer.
It's just the previous one multiplied by 2.
He said n squared. So 1 over n squared, right, would provide, if n is 1, you have 1, and then when n is 2, you get 1/4, and when it's 3, you get 1 over 9, and then 1 over 16, and then 1 over 36, right? This is a 25 first, and then 36. So it unfortunately does not match ours because it has some of the numbers, but not all of them. But you are getting closer.
Is it 1 over 2n minus n? Subtracting that?
Mm-mm. You are so close, guys. So it's not 2 times n. It's not n squared. Robert, you know it?
I think so, yeah.
What is it?
1 over n factorial. Wait, no.
No.
I was going to say 2 over...
Nope.
2 over 2.
As soon as you said 2 over, I checked out on 2 over. It's 1 over. Because you see the top is always 1, 1, 1, 1, 1. So it has to be 1 over. What is happening with the sequence on the bottom? Like, what kind of sequence is that?
The denominator just keeps getting multiplied by 2.
Thank you. What mathematical concept does that?
I don't know. You lost.
Oh, 2 to the n.
2 to the n. There we go. A-n is 1 over 2 to the n.
Christ almighty. Okay.
There we go. Woohoo. All right, so you start counting at 0, n equals 0, 1, 2, 3, 4, and make sure it fits. Does it fit?
Yeah.
Beautiful, it fits. So when n equals 0, 2 to the 0 is 1, 1 divided by 1 is 1, n equals 1, 2 to the 1 is 2, 1/2, then 4, then 8, then 16, going on. So 2 to the n. All right. So here is in blood sequences to memorize. Patterns. Number 1, n. 1, 2, 3, 4, 5, boom, boom, boom. 2n, called even numbers. 2, 4, 6, 8, 10, ... 2n minus 1, known as odd numbers. 1, 3, 5, 7, 9, ... n squared. 1, 4, 9, 16, 25, 36, ... 2 to the n, your best friend from now on. 2, 4, 8, 16, 32, ... 3 to the n is a cool one as well. 3, 9, 27, 81, 243, ... Pretty much this is all you need to know, and this is all the numbers that you guys already know, because n is the counting, even and odd numbers you know. You know perfect squares, right? You know 100 is on the list and 49 is on the list, right? So technically the only 2 lists you need to work on to kind of notice them all the time is going to be 2 to the n and 3 to the n. So you will focus your strengths, right? Your mental faculties there to get those 2. So you need to know all of these in order to be successful in transforming. And then there is another one that is very important, and I am going to write that one different color here because I want it to stand out a little bit, and that's -1 to the n. 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. That one is called alternating, as its name. Alternating, and it's very important. We're going to have alternating series. We're going to have alternating harmonic sequence, alternating harmonic series. Alternating is important because it is the only one that switches the sign between the, and is this important? Of course it's important. On and off and on and off and on and off. Positive, negative, log, hate, log, hate, log, hate, log, hate, right? It's out there, right? And we need that one. So please make sure, and here is your here is your next assignment to figure out. So get Bn formula, and here is what we are going to do. Let's go with negative 1/3 and then positive 1/5 and then the negative 1/9 and then the positive 1/17 and then the negative 1/33 ... Have fun with that. It's terrible. Now your exam question could look exactly like that one. Like there is a copy paste, 5 points, write Bn. So part A, here's the formula, give me the first 4 terms or first 5 terms, and part B, here is the sequence, give me the formula. This is the exam grade question. Let's see if you can figure it out. I'll be back in 2 seconds. Any takers?
I'm trying to figure out how to merge the two, but I know that.
Very close, very close.
1 over negative 2 to the n plus 1.
It's +1, not -1, but yeah. So because you see that, so this is why it's important to have these memorized. When you memorize the pattern of 2, 4, 8, 16, as soon as you see 3, 5, 9, 17, you immediately know that they're exactly 1 away from what you need. So if what you need is 2 to the n, and you add 1, you just generated all of your denominators, right? Does it make sense? So when you look at black arrow for 2 to the n, you see 2, 4, 8, 16, 32. What you have is 3, 5, 9, 17, 33. They're all 1 more than the perfect one. So if you copy the perfect one and you add 1 to it, you will get all of those. Awesome. Now, it's important to know that your counter n started at 1. And this is important for the top. The top is going to be -1 to the n. Now, why is it important to know where you started? Because -1 to the n, if you start counting at 1, -1 to the 1 is going to give you -1/3. Yay. But if the signs were opposite, then you would have to have n plus 1 here, right? So you have to be very careful about those kind of things. Subtle differences make the world, because all of your signs will be backwards then. So one more time, if these signs, I'll do it in orange, if this was a plus and this was a minus and this was a plus and this was a minus, then over here you would have a +1. Does that make sense? Hopefully it does. Because -1 to the 1 would be a negative, but your first term is positive. So you have to have an extra -1 to the 1 plus 1 is 2. That's going to give you a plus. So those are little things that that make these problems derail very, 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 very fast.
So we don't ever have to do the recursion?
For these problems, no, because they can be extremely tricky. If you can make them work, I mean, they can be very valuable for computer science, but math problems, it's like we usually don't.
Okay.
So now we understand the sequences, and before we go into terminology and all of these kind of things, here is the second most important thing about sequences, and that is, actually no, let's do graphing first. Graphing. AN equals 1 over n versus f of x equals 1 over x. I did tell you earlier, regard notation AN as f of x. All right? So now, what I'm going to have here is my first quadrant and my counting numbers n at 1, 2, 3, 4. We can squeeze in 5. And then I'll just put 1 and 2 on x-axis. And over here, I'm just going to draw 1 over x. We all know what that looks like. It looks like that. Let's put just y. Used to y. There we go. What you are going to find now is that when you have a sequence, you just have a dot, and then another dot, and then another dot. You do not have continuous line of dots that are all clumped together very closely. So the first in a sequence is 1, and then 1/2, and then 1/3, and then 1/4, and dot, 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 going on forever. Great. So the first one gives you 1, because when you plug in 1, 1 divided by 1 is 1. It's just a dot at 1. Then the next one is 1/2, and the next one is 1/3, and the next one is 1/4, and the next one is the fifth. Do you see how the shape of these is the same as the graph over there? If you are to connect it, you're not supposed to connect it, but let's say you do connect it, right? That's the same shape. These dots for this function and this function, the graphs will always 100% line up, except they will be dots. They will always 100% line up. But again, the difference between what you are learning now and what you know from before is that your new mathematics now is what we call discrete. Discrete meaning there's a dot, and then there's nothing going on, and a dot, and there's nothing going on, and a dot, right? The difference between, I have to bring this because some of you would play video games, typing a paper and playing a video game, right? You play a video game, you press W, and as long as the W is pressed, you are walking forward. That's continuous motion. When you're typing a paper, you tap W, and it types a single letter W, right? So the difference between taking a movie and taking a photograph, discrete, that's a snapshot in time. Click, that's your chapter 10. You took a photograph, it's just one snapshot in time, it's a dot. And then you open up your grid of photos, and there is one dot and another dot and another dot, right? A movie is continuous string of images all linked together into one continuous moving image, right? So if you want to think between typing a paper, video game, photograph versus movie, right? It is the discrete versus continuous. So those of you who are in computer science, you are expected to take discrete mathematics course. Everything is based on the discrete side because that's what computers do. Computers operate on the discrete domain because discrete is current is on, current is off, 1 or a 0, right? And that's how the computers work, which is why this is the basics for computer science, which is why a lot of people that are in electrical and mechanical having issues with this, a lot of people who are in bio and chemistry have issues with this because it's not the way you think. And this is the way how computer science geeks think, right? So for them, it's like, for the rest, it's like, what the hell, right? So two different worlds, they overlap, they're different, right? And for graphing, all you need to do is to just put a series of dots where they are supposed to be and move along. So can you graph n squared? Yeah. You're just going to put a dot at 0, and a dot at 1, 1, and a dot at 2, 4, and a dot at 3, 9, and there will be no connecting them. It will just be a series of dots, and that's it, right? Now, x squared is going to have a line going through all of those dots to connect them. Cool. Now, I want one more graph. Let's go with Bn. And this one is going to be, let's say, something simple. 2n minus 3. Nice one. So, what is my sequence if I start with n equals 0? So the first one is going to be -1, then +1, then 3, then 5, then 7, ... forever, right?
Be -3, right?
That's what I said. Please pay attention. -3 is clearly the first number. Look, I mean, come on, guys. Look. You see -3 right there? That's a -3, clearly. So please pay attention. Oh my. All right, thank you.
I think I was rubbing off on that.
So if we start our count at 0, good thing I'm not taking the test. It will be disaster again. So encouraging, huh? You are expecting the dots to form a straight line, right? Because isn't that y equal mx plus b, right? It's like 2x minus 3. So you are going to see these dots line up nicely. So we have a 0, -3. Then we have a 1 and -1. Then we have 1 and 1, and 2 and 3, and 3 and 5, and there they are, right? So they do form a linear line. Now I want you to compare the two graphs. I have to make it smaller so you can see both graphs at the same time. And I need you to see that the graph on top, n, 1 minus n, is falling down, and it's going to follow an asymptote. We know that 1 over x has a horizontal asymptote, right? So we see that this is going to fall, and it cannot fall less than 0. So in infinity, right, it's going to be 0. Where the one on the bottom is just going to go to infinity. Now we are getting to a concept of convergent and divergent sequence. Convergent meaning as you go to infinity, the y values, right, the an, will go to a certain number, the top one, 0, right? Divergent meaning as you go off to infinity, it will, the bn, for the second example, would go to infinity. So now we get into this convergence versus divergence. Which we label C and D for simplicity. And here is, in blood, the first out of 11 tests that you will be memorizing in this course. Test for convergence of sequences. Here we go. If limit as n goes to infinity of an equals L, then sequence an converges to L. Otherwise, an diverges. Put this on a cloud. At this point in time, I will recommend that you keep track of these on a cover of your notebook, right? The cardboard cover of your notebook, or a separate sheet of paper. I will be providing you with, I don't think I have them with me right now because we are not yet deep enough into this stuff. But at least in the beginning, for you to, I wanted to show you a sample, and I don't think I have it. Usually I have a leftover somewhere that I can show, but I will be providing a sheet of paper that will have all of them nicely in a chart. But it's good for your own sake and purpose now to keep them organized somewhere until I bring that sheet, which is next class. I mean, I'm bringing that thing next class, because next class will be far enough for you to use it. Again, it's going to be 11 of these things. One for sequence and 10 for series. Yeah, I don't have them with me, unfortunately. I was hoping to see at least one. I just took them out and put them in my office on a pile. All right, cool. So now, here we go. Test for convergence. an equals 3n plus 1 divided by n squared minus 1. What are you supposed to do?
Build the sequence first.
Nope.
Hopital.
What does the cloud say?
Find the limit.
Find the limit. That's it. This is why you are memorizing the cloud. Cloud says to test for convergence, just find the limit of the problem. Now, the method you're going to use is your problem, right? The only thing that this section is asking you to memorize is that to test the convergence of the sequence is to take the limit. So, to solve the problem, you must take limit n goes to infinity of 3n plus 1 over n squared minus 1. Now, what kind of witchcraft you're going to use to solve this, that's your Calculus 1 problem, right? So, you're going to go with the growth rates, you're going to go with the L'Hopital, you're going to go with remembering in Calc 1 section 2.5 that when you have polynomial divided by polynomial, you can divide everywhere by the highest power. We can solve this in 3 ways that I can think of. L'Hopital is 1, divide by n squared everywhere is 1, and the growth rate being that you're dividing linear by a quadratic. Quadratic is faster. All of them must give you 0. You have to know Calc 1. Otherwise, it's going to be 0 on this test. I mean, every problem is a limit problem, right? So, let's do the L'Hopital first, because this is infinity over infinity. L'Hopital will give us limit n goes to infinity of 3 divided by 2n, and that's 0, because you are dividing a finite number by infinity. We just saw, right, I had that experiment done where we had that one big piece of paper, and as you keep dividing it, right, it turns into confetti and then into nothing. You can also, or use 2.5, the limit n goes to infinity of 3n over n squared plus 1 over n squared divided by n squared over n squared minus 1 over n squared to solve it. This is what you have from there. So that's 3 over n, which is infinity, plus 1 over n squared. Hold on, send. Got smudged. There we go. Divided by 1 minus 1 over n squared. So now all of these go to 0. And you just get 0 divided by 1, which is 0. So that's another way. Or growth rate, limit n goes to infinity, linear divided by quadratic, which is limit. I mean, this is terrible notation. This is you thinking, not you writing. This is terrible. Of slow over fast, which is that, right, terrible thing I wrote earlier, equals 0. Right? So these are your 3 ways to solve the same problem. All we are looking for is the answer, which says an of 3n plus 1 over n squared minus 1 converges to 0. That's the answer we are looking for. Now, and no one cares which way you took the limit. right? So whatever makes you happy, I just need that 0 at the end. Converges to 0. Next example. At this point, I'm just going to put a whole bunch of these from the textbook. I just need to get there. There we go. Beautiful. And some of these are just absolutely insane, but let's start on the easier side. So let's say your Bn is 2e to the n plus 1 divided by e to the n. What happened?
It's just infinite.
Why?
Because it's going to be infinite growth over infinite, over infinity on the bottom. Same growth rate.
Isn't it 2? You just do L'Hopital's or wherever.
Didn't I just say retire common sense? The first thing I said. Retire the common sense. Please, guys.
So in that case, you just divide e by en by en.
All right, so
Oh, that's what I was gonna say.
limit n goes to infinity. And you have 2e to the n plus 1 over e to the n plus 1. And as I said, I don't care which way you do it, just do the math. No gut feelings, please, and no common sense. Retire it. So let's do it two different ways. You want L'Hopital? Here it is. L'Hopital, limit n goes to infinity. And when you take the derivative, you get 2e to the n plus 1 dies. Divided by e to the n, these guys cancel, limit is 2. Awesome. Or, you don't want to do L'Hopital. Sometimes you will have to use L'Hopital's rule. You will have to. In this case, there's another way. You said divide by e to the n. I like it. I like it. Divide by e to the n, divide by e to the n, and the reason why you are allowed to divide by e to the n is because e to the n is guaranteed not to be 0. E to the x is always above x-axis. It's never 0, so you can always divide by it. Can you divide by sine? No. Sine is 0 infinitely many times. You can't divide by sine, but you can divide by e to the n. Awesome. So this turns into a limit. N goes to infinity of 2 plus 1 over e to the n divided by 1. Now, when you divide 1 by infinity, that's going to shoot to 0. 2 divided by 1 is 2, and there's your 2 again.
Yeah, I know you're looking at me.
Yes.
Yeah, I skipped some steps.
I have to have that scapegoat, right? And now that's you. No common sense anymore. That's it. Guys, you want to do very well in this section. Here's your cloud right here. You got to know that one. And when the question says test for convergence, oh, I'm taking the limit to infinity. And now let me do the limit because, right? Okay, here's the next one to make things much more interesting. Let's say that Cn is given as 2 to the n plus 1 times 3 to the negative n. Wonderful problem. Did you do the math?
I did it in my head because
I don't want to talk.
N is gonna go on the bottom.
I don't want to talk. Did you do the math on paper?
Yes.
I don't want a math in a head. This is it. I want you to empty heads.
But I don't have common sense anyway, so that's why I think I know where it's going.
Okay.
The limit's gonna turn into infinity over negative or over infinity.
So we have to use Hopital.
Yeah.
Of some sort. Okay, good. I'll give you
stop
that.
in there.
Okay. All right. Now it's time to start writing.
That's what I did in my head.
Okay, let's take a look at this together. Is it a living nightmare or not?
Is it 0?
I don't think so. I don't know, let's see. Might be. Might be. Limit n goes to infinity, and I'll just put 2n plus 1 over 3 to the n because that's what it is. Now, I don't like that plus 1, so I'm going to peel off one of the 2's to bring that to 2 to the n. And what I can do is kick that 2 completely in front of the limit and just have 2/3 to the n. And I need to take this limit. So whatever this limit is, I'm going to multiply that by 2, and I'm done. So now I just need to solve this limit. Now, what I have here is something that I can solve using a logarithmic differentiation, because I can define this as y equals, leave some space, 2/3 to the n, and we can stick ln's on both sides. Then have the ln of y equal to n times ln of 2/3. Right?
How did you change that to y? Can we talk about that 1 second?
I didn't change. I define what I want to calculate. I define it as y. That's the logarithmic differentiation. Taking the logs to solve the limits. Not logarithmic differentiation. Sorry.
Totally okay.
Use the wrong terminology there.
I'm still confused either way.
So I want to find the limit of this. So I just copied it here, and I set it equal to y, because I'm going to say that's my function that I want to find the limit of. So I ln both sides, and what I have is this. So what do I do now?
You could differentiate using property.
No, I'm not differentiating. I'm taking the limit, right? So when I take the limit of n goes to infinity, what do I get on this side? I get infinity, right? Does this make any sense?
Yeah, I get it.
Actually, let me write it then differently. Let me try a better approach. Because if this is going to be confusing, then so let's write y is equal to the limit n goes to infinity 2/3 to the n, because I don't know what the limit is. I'm just going to call the whole solution y. Okay? So now I'm going to put ln on both sides, and now I have to invoke theorem from advanced calculus, which says that limit and ln can swap sides because ln is the increasing function. So limit n goes to infinity of ln of 2/3 to the n. So now ln y is equal to the limit n goes to infinity, and then I have n drop in front, and I have just ln of 2/3. Now, when n goes to infinity, the whole thing goes to infinity. So now I just have that ln y equals infinity.
I don't understand why you can't just, at the very beginning, when you put it as 2 to the n plus 1 over 3 to the n, why can't you just, it becomes infinity over infinity. So wouldn't that be 1?
You have to take the derivatives. But derivatives would always be, derivatives will always be 2 over 3, 2n to the 3n and then times ln and so on, so they will never actually go away. So that way of L'Hopital solving, yeah.
Okay.
That makes sense?
Yeah, thank
Okay.
you.
All right, so now what we do?
Once you get 2/3 to the n without taking the ln of both sides, like if you multiply 2 a bunch of times, it'll be getting infinitely bigger, but at a much slower rate than if you multiply 3 a bunch of times. So how is it not 0? Because isn't the bottom getting bigger faster?
But they're both the same type of function. They're both constants, or they're not. What it would have to be 2 over 3n or 3 to the n.
It's because they're
It
both
has to be a greater power of a function, right?
So
You know what we are going to break our heads very soon with? How much is 1 plus 1, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1? And the answer will be hell no.
is it 1/12? Technically.
No.
Ridiculous like that.
What?
I know. It's gonna be amazing. That's why. What is the first sentence of this of the chapter?
Forget common sense.
Good. Thank you very much.
I don't have any, so this shouldn't be a problem. Oh my god.
I know. All right, troops. So, I have this n plus 1. I will peel off the plus 1, and that's where this 2 comes from, because that's 2 to the 1. And if I am to multiply them, I will get n plus 1. Then I am going to kick that 2 in front of the limit, because that's just a constant that multiplies everything, and not worry about it anymore. I still am looking for the answer to plug in over here, but I have to find the limit of this first, which is this next row over here, where I set that limit to y, because I want to calculate the value of the limit. There we go. So, do you understand all of these so far?
The only thing I missed was just moving the 2 out. I wasn't thinking about just moving the plus 1 as a 2 being multiplied into it. Because obviously, I'm just not used to moving it around as that 4. But no, everything else makes sense. Because I did the same thing, I didn't do the same thing, I just made a mistake at the beginning where I took ln of both of them and ended up getting 2/3 anyways.
Mm-hmm.
It's just not infinite. Because I made a couple mistakes.
All right. So what now?
My brain hurts.
Your brain hurts.
It does. It always hurts.
So then this is divergent.
Hold on. We have ln y is going to infinity. It's ln y goes to infinity. So when see, guys, if you draw ln graph, trying to see where I can get what I'm looking for. This needs to be a 0. I need this to be negative infinity. I am missing something somewhere. I can't see it right now.
What ln 2/3 is a negative number. So when you multiply it by infinity, it'll always be negative.
Yes. Oh my God. ln of 2/3 is the negative number that goes in here. That's what I was looking for. Now look, when ln of y is negative infinity, that's happening here. So what's the answer to it? It's coming from 0, right? So this limit is 0.
Okay.
And then you have 2 times 0. Answer is 0. Yes. Now, we are not going to do this every time because we are going to have something that's called geometric sequences and geometric series. And you will simply learn that r to the n, if r is less than 1, convergence, r bigger than 1 or equal to 1, divergence. But that's not there yet. Right now, we just did this calculation because, I'll write this 2 more times in a red, so don't worry about it. I just want to tell you that the preview is coming up.
So are you saying the graphs is saying negative infinity while the solution?
So the answer, yeah.
So it should be
negative infinity.
No, but once you raise it to e, so it's y equals e to the negative.
Okay. You can, yes, we can definitely do e and e.
So then it becomes 1.
And then it becomes y
And then that's
is equal to 0. And because we defined that y was the limit as n goes to infinity of 2/3 to the n, then that has to also be 0. And then we have the 2 times 0 equals 0 for the whole.
So the limit is not negative infinity anymore?
But you had ln y on this side. So you defined your limit that you're looking for as y. You had ln y is negative infinity. You didn't have y is negative infinity. You had ln y is negative infinity. So we have these 2 methods in Calc 1, one for limits and one for derivatives, and they work the same way. If you can do something easily, you use ln both sides, but you have to undo lning, right? Because you added ln from nowhere. Eventually you have to e both sides to kill the extra ln. So that's where that negative infinity turned into 0, because I still need to remove the ln from the left. So, it's like add and subtract the number. In this case was apply ln and then remove the ln for the ease of calculations. So this was a tough problem if you don't know the shortcut for it. The next talk, I see a whole bunch of problems with factorial.
But you have to go through all those layers to know that
No.
n is equal to 0, because you could have said as the limit goes to n goes to infinity, and 2/3 to the power of n is really 2n over 3n. And when you put the
Again, they are of the same. The answer to your question is yes, you are right. But it's easy to see it for 2 to the n and 3 to the n. It's harder to see it for polynomials, it's harder to see it when you have mix of functions and so on. Knowing the procedure is important for problems where you can't make that argument. That's the problem, right? So I agree with you, and I did show you, and then erased it, that we are going to say if the fraction is 1 or bigger, it's divergent right away, right?
right.
The answer is going to be infinity, and if it's less then it's not. But
If the fraction
Convergence.
of the integers.
yes, so in this case was 2/3.
Okay. Yeah.
It will always converge for 2/3.
Okay.
And 3/2 will diverge, right? So we are going to have that as a rule, and you will not have to go through this. But that doesn't apply to all other examples that you can run into, which is...
Okay, so you could just go straight to it and get that answer, but
Yes.
every one of them is the same. Okay.
Okay, good. Let's see. Problem 35, you're gonna like. AN is equal to tangent inverse of n. This one, I'm literally giving you 17 seconds. That's all it is. "13 seconds left.
So long, 10 seconds.
I know. There's a crisis. One of my friends can't play the game. Monitor stopped working. All right, so we have the tangent inverse. What is the limit as n goes to infinity for tangent inverse of n?
Pi over 2.
Done. So answer converges to pi over 2. Awesome.
Is there a way to do that mathematically without just like knowing what the graph is?
No, you know what the graph is. It's actually mathematically is done through the inverse of you are swapping domain and the range from between the graph of tangent and the graph of inverse tangent.
Graph of tangent, it's infinity at pi over 2.
Yes. So you're yes.
I was thinking it was that, but I just have not done anything with tangent inverse, or anything?
So you would do this, right? This is your tangent graph, and it has the vertical asymptotes at negative pi over 2 and pi over 2. When you swap domain and range, it becomes a sideways graph, because you are literally swapping. That's what the inverse is. You're swapping domain for a range, and it looks like that. So that's mathematically proving it that works.
So sine, cosine, and all the other fun ones are similar in that regard?
Mm-hmm.
The inverse is just flipping that. Okay.
Should we do some of the more interesting? Oh, here's another simple one that, Bn is equal to 1 plus 4 over n raised to the 3n. So for some of these that look like this, I know the answer just by looking at them, because professional deformation, right? So you either know the answer instantly, or you have to do the ln thing for about an hour. So put the limit equal y, ln both sides, strip that 3n. Now, I did ask you to memorize this particular limit sometime in chapter 7. It should look familiar. I think it was chapter 7. So the limit to test the sequence, right? We do the limit 1 plus 4 over n to the 3n as n goes to infinity, and the answer is obviously e to the 12, so converges to e to the 12, and that's it, done.
What? Where'd you get e to the 12 from?
I pull it out of magic hat.
That's literally what it feels like in my head.
So what do I know? Because, again, professional deformation, right? I know that the limit when n goes to infinity of 1 plus a over n to the bn is going to be e to the ab. Right? That's
Oh my god, okay.
that's what I know. Now, the definition for number e is 1 plus 1 over n to the n. So no a, no b. When both of those are 1, you get just definition for e. And that's the one that I have memorized because, again, this is what I do. Now, if you want to prove this, there I say you simply set it equal to y. Leave some space. And then it's called proof by intimidation. Then you ln both sides.
Just stare at it until it tells you how.
And then limit goes to infinity. You have your 3n ln of 1 plus 4n. And when you plug your infinity in, you get infinity times 0. L'Hopital rule for infinity times 0 is going to use the trick 1 over f. So again, depends on your knowledge on L'Hopital, which is why you should be reviewing this. You can go back, take a look at my lecture for 0 times infinity and so on. And we are going to have ln of 1 plus 4 over n divided by 1 over 3n. So that's when I take 3n and I put it in the denominator, but if I want to put 3n in the denominator, I have to put it as 1 over 3 to the n, because you have to use it. That's how we use the trick over there. So now I have 0 divided by 0, and which is the L'Hopital rule, right? When you plug in infinity, 4 over infinity goes to 0, ln of 1 is 0, and then 1 over infinity is 0, so 0 over 0. And at this point, we can use L'Hopital, which is we are going to differentiate numerator and denominator independently of each other. So denominator is easier. Derivative of 1 over n is negative 1 over n squared, so negative 1 over 3n squared in the denominator. And to differentiate the numerator, well, it's ln, so you will have the derivative of this times the derivative of the inside. So the derivative of ln is 1 over 1 plus 4 over n, and then the derivative of the inside, there will be times, is going to be negative 4 over n squared. That's a chain rule. So a little bit convoluted, but we can deal with it. Multiply everywhere by 3n squared to get rid of the negative 3n squared, to get rid of the bottom fraction completely. So I have limit n goes to infinity, and then over here the denominator cancels completely. I have 1 over 1 plus 4 over n, and then negative cancels the negative, n squared cancels the negative, so I just get 12. You can see the 12 forming, right? So now when I take the n goes to infinity, this puppy will go to 0 because you're dividing 4 by infinity. So the whole thing happens to be ln y is 12. And if ln y is 12, when you e both sides, you get that the limit you were looking for, y is equal to e to the 12. So now, for the answer for the problem, we would say, what did I use? Bn, an, bn. So Bn equals 1 plus 4 over n raised to the 3n equals to, sorry, not equals, converges to e to the 12. Now, if you like formulas and you like, again, why do I know this? Because I use it every semester for the last 12 years, right? So obviously I'm going to know the two definitions. I am going to, let's go blue. So limit n goes to infinity of 1 plus 1 over n to the n is e. And the supercharged version is 1 plus a over n to the bn is equal to e to the ab. So for me, when I look at this problem, all I need to do is to multiply 4 times 3 is 12, and I know it's e to the 12, and I'm done. But I know what I'm looking for, right? So one more example, and then we'll put some definitions, and then we're done. So this example is going to be an is equal to n sine 1 over n. This was on the exam last year, exam 3. All right, so in order for us to write the properties and the theorem, after this, we gotta speed up the process a little bit. You can do the same trick with ln both sides and you know, all of that stuff, because you have, as you can see, you have infinity times 0, and then you use the trick, right, and all of that. So let me actually write it here. So in parentheses, we can use infinity times 0 with f equals 1 over f dot dot dot, right? So that stands. If you took those steps, you are 100% correct. What I want to do is I want to, you know, flex a little bit here. We're going to use U substitution to solve this problem, where I don't like sine of 1 over n, so I don't like 1 over n. So I'm going to substitute as u equals 1 over n, right? Because clearly u is upside down n, right? So that's a good. So u equals 1 over n. There is no du here because it's not calculus in terms of integrals. It's just basic substitution. So now my problem is limit. Oh, and by the way, if I write 1 over u equals 1 over n, then n has to be 1 over u because they're opposites of each other, right? So n is 1 over u goes to infinity, and now I have 1 over u for n times sine of u, and if 1 over u goes to infinity, then u must go to 0. So limit u goes to 0 of sine u over u, and that's 1. Awesome. You can prove this one by using L'Hopital derivative of sine. It's cosine, a derivative of u is 1, so you have cosine of 0, which is 1. 1 divided by 1 is 1. So very easy to prove this, but generally, you know, people have this one memorized because it's frequent. So answer, an equals n sine 1 over n converges to 1. All right, so let's just put some theorems and call it a day. It's some of this stuff is common sense stuff. Some stuff obviously will be you learning the words, and words will make sense when you hear them, hopefully. So we have the theorem which has the limit of an plus minus bn as n goes to infinity will be equal to a plus b, meaning that if you have multiple terms inside, you would have to deal with each one. These are technically limits laws from 2.3 repeated, same ones, just condensed. Limit of can will be ca as n goes to infinity. So if they converge, right, they do all of these things. There's no product rule, so we just do it straight. An times bn would give you a times b. So no product rule and no quotient rule, which is the end of the list. An over bn is equal to a over b, provided that bn is not 0, provided that b is not 0. Cool. I just need to get to the second part of this. Oh yeah, control minus.
Why is it like capital on the right? Is it still the same?
Limit n goes to infinity of an is the a. I used L in a definition, but since I have two of them, and then limit n goes to infinity of sequence bn is a finite value b. So in our case was pi over 2, was 1, was e to the 12. So that's what those numbers represent. Okay, so now I just need to, I mean, I could tell you go and read, but I have to write these guys down because let's go blue, because the wording is necessary. So definitions. Now this is not definition of sequence or anything. It's just definitions for words that you're gonna see. So an is increasing if an plus 1 is bigger than an. So any term you pick that it's further down in a sequence, if that term is bigger than the previous, any of the previous terms, right, it's going to be increasing. And an is non-decreasing if an plus 1 is bigger or equal than an. See? Just some English language. It makes sense when you see the mathematics, right? Then we have an is decreasing if an plus 1 is strictly smaller than a previous term. So if the terms are getting smaller, it's decreasing. And now we're going to have an is what? Non-increasing. If an plus 1 is less or equal than an. We have three more. An is called monotonic. So an is monotonic. If it is either non-decreasing or non-decreasing. Either non-increasing or non-decreasing. That's monotonic. An is bounded above if an is less than equal to some value m, so no values go above that. An is bounded missed the n. There we go. Dead below if an larger or equal than, they use n from below. And finally, an is just bounded if bounded above and below. That's your inverse tangent, guys. Bounded if it is budded from above and below. And I'll give you an example for this one is tangent inverse of n, because when you graph it, you're going to have dot, 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 dot. There we go. So that's what a bound means. You have a bottom bound and a top bound, and the sequence is squeezed in between. Bounded below would be, a great example would be E, right? Because, well, E to the n, right? So it goes like bu, 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 bu. It's bounded below and it goes, shoots up, right? And you can come up with examples. I mean, there are a whole bunch of examples that you can worry about. And last theorem that we are going to write, and this theorem, once you study all of these terms and terminology, when you see this this theorem, it will make perfect sense. A bounded monotonic sequence converges. So if you have a bounded monotonic sequence that converges, and here are the two graphs that will help you understand it quickly. If you pick an upper bound of some kind, so this is your M bound because the bound above, and you have a sequence always increasing, then it will be always approaching that bound, and it will converge to M. So this one will converge to M. Now, if you have a lower bound and you have the sequence go down, monotonic means it will always go the same way. It's always increasing or it's always decreasing. That's the word monotonic from the previous set of words. So if it's always decreasing, then it cannot turn up to decrease, so it has to converge. And in this case, if this is n, we'll say converge to n. Unbounded sequences diverge. Unbounded sequence diverge. That means shoots to infinity. There's no bound. There's nothing to prevent it from shooting to infinity. So that's the introductory lecture. Next time we are going to have exam review, and we are going to continue with 10.3, 10.4, maybe even 10.5 depending on the time. Probably not. We are going to learn for the rest of the chapter something is called series. Series, very simple definition, sum of a sequence. So now the question is, when you sum infinitely many numbers, do you always get infinity? Or sometimes they add up to a finite number, which is where we're going to break our head with minus 1 plus 1 minus 1 plus 1, right? Because when I add infinitely many of those, I know what happens when I add 7 of them because I can test that on a calculator. Well, don't need the calculator for plus 1 minus 1, right? But what happens when I add infinitely many of those? What happens when I add 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6? What happens when I add those guys squared? What happens when I add a to the n squared? What happens when I do the 1/2 to the n, and so on? So the rest of the chapter deals with all of these other functions that are used in signal processing and computer science later on to build some really powerful stuff. So next 2 meetings, which is next week, and then we have next week have half of series next week, and then the review. The following week is the exam, and after exam, we'll finish chapter 10. Then the next class, chapter 11, only has 4 sections, and those 4 sections are 1 and 3 are the same section, and 2 and 4 are the same section, actually. So technically you can mush the entire chapter 11 into 2 lectures, which is sometimes I do it, sometimes I don't. We are done with chapter 11, and chapters 10 and 11 is exam 3. We are left with 5 classes, and then the 6th meeting is the final. Let me stand closer. We are left with 5 classes in which we are going to have 2 exams, and then the 6th class is the final. All right. Just wanted to make sure that everyone heard that.
It's a good thing this stuff is so easy, right? I'd be worried.
Yeah. Oh my
I know, exactly. Bye.